So today we're going to be using the knowledge that we gained from Chapter 1 in minerals to expand upon that and talk about the different types of rocks. And on the Earth we have three different rock types. We have igneous, metamorphic, and sedimentary rocks. But we'll see that all of these different types of rocks actually cycle back and forth throughout time across our planet. And this is known as the rock cycle. Through different types of geological processes, we're going to take one type of rock and then transform it into a new, different type of rock. But here we see three different types of rock. But what's going to be most important is that for each individual type of rock, there are going to be very specific processes to form them. So for example, if we look at igneous rocks, for example, all igneous rocks form from the cooling and solidification of lava or magma. Basically, this lava is going to get colder, it's going to turn into a solid, and then be an igneous rock. We're also going to have sedimentary rocks present on our planet. So think about like the Grand Canyon, where you can see these nice clear layers of rock stacked one on top of another. So these sedimentary rocks form from pre-existing rocks being broken down into smaller pieces, and then basically all of those smaller pieces being glued back together as a new sedimentary rock. Now our third type of rock is called a metamorphic rock. These generally occur inside of the Earth because it takes a lot of pressure and heat to metamorphose or change these rocks into a new type of rock. So with this rock cycle, we're just taking one type of rock and then transforming it into a new type of rock. And whatever processes are being used, whether it's lava cooling down and turning into a solid, or heat and pressure, is going to determine what type of rock forms. So again, with this rock cycle, we're just changing one type of rock into another type. But we're going to be able to transform any type of rock into any other type of rock. Again, as long as those necessary conditions are there, like the cooling of lava for igneous rocks, or the intense heat and pressure for metamorphic rocks. So it doesn't matter what type of rock we have, as long as it follows those geological processes to form a new rock, any rock can be transformed into any other type of rock on our planet. So we might think of rocks as being stable. If we look at rocks, maybe out in our backyard, they don't really change from day to day. But if we look at rocks on a geological time scale, over millions and billions of years, we're going to see that rocks are constantly changing. They're not only being weathered or broken down, but they're going to be changing from one type of rock into another type of rock through the rock cycle. But the changes in our rock cycle don't happen on a human time scale. It happens on our geologic time scale when we're talking about really long periods of time. But depending on where we are on our planet, we're going to see different stages of that rock cycle. So we might see igneous rocks forming in places like Hawaii, where we have a lot of volcanic eruptions, producing lava on the surface, where eventually that lava is going to cool down and turn into new igneous rocks. We're also seeing that around the Gulf of Mexico, that a lot of sedimentary rocks are forming. And this is because the Rocky Mountains in Colorado are being eroded. Those really nice sharp peaks in Colorado are constantly being eroded, where they're becoming rounder and rounder. And all of that broken off rock material is eventually going to be carried off into the Gulf of Mexico, where it's going to be deposited and then eventually kind of glued together as a new sedimentary rock. And the third example are the Himalayan mountains. We see that these mountain ranges grow every single day about the same rate that our fingernails grow. But in order to form these mountains, we're going to have extreme pressures involved, thereby forming new metamorphic rocks. So different places on our planet, we're going to see different types of rocks developing. But again, we need those geological processes to occur to form either igneous, sedimentary, or metamorphic rocks. But if we were to look at our rock cycle, it might look like there's a specific order that these rocks need to go through. If we went back and looked at that chart, it would show that it always goes from igneous, sedimentary, metamorphic, back to igneous. But this isn't the case. Again, we can take any type of rock and transform it into another type of rock. So it doesn't always have to go through that exact cycle. But we're going to see that the reason why we have this rock cycle is because at the center of our Earth, it is extremely hot. Our core, we're talking about thousands and thousands of degrees. So it's going to move around the magma inside of the Earth. But we also have a lot of external processes that affect our planet. Things like weathering, where literally weather, things like wind and rainfall over those millions and billions of years are going to break rocks down into smaller pieces. So the combination of the Earth having a really hot inner core and us having weather on our surface is going to continue this rock cycle. So now we're going to get into the three different types of rocks and how they form, and then some of the more common examples of these different types of rocks. We're going to start off talking about igneous rocks, then move into sedimentary, and finally end with metamorphic rocks today. So with our igneous rocks, these are the ones that literally mean formed by fire. Here we're going to have lava or magma. It's really hot, melted rock material, cooling off over periods of time and solidifying, turning into a solid rock, which at that point it would be called an igneous rock. So we see that these igneous rocks form just from lava or magma that cools down, and the minerals are going to start to crystallize or grow within these rocks. So here there's going to be a big differentiation between lava and magma. Both of them are molten rock material, just rocks that have been melted down. But magma is going to be this melted material as long as it's still inside of the Earth. Lava is going to be magma that's reached the Earth's surface. So, for example, if a volcano is erupting, it will be erupting lava because that molten material is now on the surface of the Earth. Before it erupts and it's still stored underground beneath the volcano, it would be magma. So here the difference between lava and magma is just where is it? Magma is inside of the Earth, while lava is on the surface or outside of the Earth. But we're also going to see that our magma and lava is always trying to rise towards the surface. And that's because this is melted material. It's fluid. And therefore it's going to be less dense than the surrounding rock inside of our mantle. So think about a lava lamp. At the base of the lava lamp, there's going to be a heater, and it's going to start heating up the lava at the bottom of your lamp. And eventually, when that lava gets hot, after it's been on for like a half an hour or so, that lava, because it's been heated, it's going to become less dense. It's just going to rise to the top of your lava lamp. And we see that the magma inside of the Earth does the exact same thing. If we go from the surface of the Earth down to the core, right in the middle of our planet, it's incredibly hot. It's going to heat all of that material surrounding the core, causing that hot, less dense magma to rise up towards the surface and eventually be erupted as lava. So we're going to see different types of igneous rocks forming, depending on whether it's forming in or outside of the Earth. So if we have lava cooling down, again, lava is always going to be on the surface of our planet. If we have lava turning into a new igneous rock, these are called extrusive or volcanic rocks, because generally we're going to find them forming around volcanoes. And at least when I was learning this, I remember that extrusive rocks is lava that has exited the Earth. So again, we're going to see that most of these extrusive igneous rocks are forming around volcanoes. But if we're watching like a Michael Bay or a rock movie, he seems to have a lot of those dealing with geological hazards. We might see that in the movies, these volcanoes are shown as really violent eruptions, where things are just thrown in the air and things are exploding. But 90% of all volcanoes on our planet aren't violent. Instead, they're going to be very gentle, volcanic eruptions, where the lava is just simply going to slide down the side of the volcano, kind of like a river, but replacing all that water with very fluid lava. But we're going to see these types of rocks forming in very specific parts of our planet. Some entire islands, like all of the islands of Hawaii, are just volcanoes that over numerous eruptions have spilled a lot of lava on the surface. Eventually that lava is going to cool down, turn into new igneous rocks, and therefore new land around Hawaii. But even on the continental U.S., we're going to see that in the Northwest, specifically Washington State, we're going to have a lot of volcanoes that are present. But those are our extrusive rocks, the ones that form on the surface from lava. We're also going to see intrusive igneous rocks developing as well. And here these intrusive rocks are forming inside of the planet. So here these are forming from magma that has never touched the surface. Instead, this magma is cooling off and turning into a solid inside of the earth, an intrusive igneous rock. But these are going to be a lot rarer because since they're forming inside of the earth, something has to happen to push them up to the surface where we live. And this is called uplift. Something that's going to literally lift up these rocks towards the surface where we can see them. So some of these are relatively close by, like Stone Mountain in Georgia is one giant piece of granite, an intrusive igneous rock that formed deep underneath the surface and then was later pushed to where we live. But other famous examples are Mount Rushmore, where the president's faces have been carved as a cliffside, as well as Yosemite National Park in California. So we're going to see that as we go from magma or lava to the solid crystalline rock, we're going to see that crystals are going to start forming. Basically, minerals are going to go from these ions, these dissolved elements inside of the magma. And once that magma starts cooling down, they're going to start growing into solid individual crystals. So think about trees. If it's a new tree that's only maybe a couple years old, it's only going to have a couple rings if you could look inside of that tree. But if we were to look at a tree that were 100 years old, if we could look inside of that tree, we would see 100 rings. Because each year, those trees are just going to put another ring down, growing larger and larger over time. We're going to see that crystals are going to develop in a very similar way. Newer crystals are going to be very small in size, but as they continue cooling off, we're going to add more and more of those ions, those dissolved elements around the outside of the crystal. So over time, these crystals are going to grow larger and larger the longer they have to cool off and continue growing. So we're going to see that the size of our crystals, just the size of the minerals inside of our igneous rock, are going to tell us how quickly or how slowly that lava or magma cooled off. So if we're looking at magma inside of the earth, if we were to go inside of the earth, it's still thousands of degrees. It's very, very hot. So it's going to take that magma thousands or millions of years to cool off and solidify. Because it has so long to solidify, that means that the minerals inside are going to have a really long period to grow. Therefore, we're going to be able to see those minerals with our naked eye. So if it cools off really slowly inside of the earth, we're going to have these really obvious minerals that we can easily see. But if we have lava escaping from like a volcano, that lava, let's say it's 70 degrees outside, it's going to cool off from that maybe 4,000 degree lava, being in contact with 70 degree air very, very quickly. Because the lava is cooling off quickly, that means that the minerals inside of it aren't going to have enough time to grow. So this quick cooling of lava on our surface is going to result in really small crystals, like we can see here in the second image. It just looks like a matte black rock. So here, there are still minerals inside of this rock, but the minerals are so small that we would need a microscope in order to see them because they cooled off very quickly along the surface. But we're also going to have special cases of cooling, such as instantaneous cooling. So if we were to drop really hot lava into really cold ocean water, that cold water is basically going to shock that lava into solidifying instantaneously. So this doesn't mean that a few seconds has passed. Literally, the instant that lava touches cold water, it's going to shock it into being a solid. But this instant cooling is very unique because since it formed instantaneously, there's been no time whatsoever for the minerals to grow inside of that lava. So therefore, if we see a glassy igneous rock, it tells us that it formed instantly, and there are no minerals whatsoever found inside of that rock. But we're also going to see that the types of minerals, and therefore the crystals in our rocks, are going to depend on what kind of stuff is available inside of that magma. We're going to see that some magmas may have a lot of calcium, whereas others might have a lot of magnesium. But it's also going to be dependent on how much dissolved gases are inside of our lava or our magma. So we're going to see that most of our igneous rocks are made up of those silicate minerals, the ones that have both silica and oxygen inside of them. But in addition to those two elements, we're going to see a lot of aluminum, calcium, sodium, which is Na, potassium, which is K, magnesium, and iron, which is Fe. Together, these few elements make up almost 98% of all of the magma found on our planet. But we're also going to see that there are some trace elements inside of these rocks. And here the word trace is important because it's going to be very, very small amounts of these elements inside of our rocks. These are going to be a lot of our very expensive metals, things like gold, silver, and uranium. But we're going to see that overall, we're going to form two different groups of these silicate minerals inside of our igneous rocks. And it's going to depend on whether we're seeing more salts or more metal elements inside of these crystals. So if we're looking at these dark silicates, they're going to be darker in color, and they're also going to be heavier in weight. And that's because these dark silicates have a lot of iron and magnesium inside of them. Both of these are metals. And if you've ever held something that was solid metal, it's very, very heavy. So we're going to see that dark silicates, again, they're going to be darker in color, as well as being heavier in weight because they're going to be full of metals. But we also have light silicates, where these silicates are going to be lighter in color, and they're also going to be lighter in weight because now they're full of things like salts. We're going to see potassium, sodium, and calcium inside of them, as well as a lot of silica as well. So since this is full of salts and not metal, they're going to be lighter in color as well as lighter in weight. And we're going to see very specific types of minerals developing inside of these, whether they are light or dark silicates. So we're going to be able to break down our igneous rocks into different groups based on what type of minerals we see inside of them, whether they're primarily light or dark, a combination, or even green. So this chart is just summarizing the different types of rock groups that we can have within our igneous rocks. So here on the left-hand side, showing the pink, these are our lighter silicate minerals, those ones that are full of salts. So they're going to be light in weight as well as light in color. We're going to call these rocks felsic or granitic because granite is one of the most common types of these light-colored igneous rocks. But we're also going to have dark-colored igneous rocks. the ones that are full of metals, so that they're darker in color and heavier in weight. These darker colored rocks, we're going to call them either mafic or basaltic, because we'll see that there's going to be a very dark colored igneous rock called basalt as well. But there's going to be an intermediate between these light and dark rock groups. So these intermediates, it's going to be a combination of both light and dark minerals. It's not going to be one or the other. It's going to be a combination of both. And we're going to call these intermediate or andesitic rocks. So here it could be like a 50-50 ratio of light to dark rocks, or it just might be a medium shade of gray that's neither a light gray or a dark gray in color. And then finally, our last group is called ultramafic, which is found here on the right. Ultramafic rocks are going to be very unique because they're going to be green in color. And that's because they're predominantly made out of one mineral called olivine. Olivine is olive green in color. And that's because it has so much iron inside of it that it's just going to be a dark green. So anytime you see a green igneous rock, it's going to automatically be ultramafic. It just has a ton of iron inside of it, causing it that green color. So now we're just going to go over each of these groups individually in a little bit more detail. So our first group, again, are those felsic or granitic rocks. These are the ones that are made up primarily of those light-colored and lightweight silicates, the ones that are full of salts. So the reason that it's called felsic is that it's just an abbreviation of feldspar and silica. Feldspar being the most common mineral inside of these. If we were to look at a piece of granite, the feldspar are going to be these kind of very light pink colored minerals. And we also see a lot of silica inside of these. But even though we're calling these light colored rocks, if you look at this image, you'll notice that there are some black minerals inside of this as well. So we will see that these felsic or light colored rocks do have some dark colored minerals inside of them. But generally it's going to be less than 10% of these darker colored minerals. So overall, the majority, about 90% of the minerals inside of this rock are white in color, and therefore we're going to call them felsic. So these felsic rocks are unique because they are predominantly silica, or half of that necessary elements to form silicate minerals. So with these felsic rocks, we're going to see that they make up the majority of our continental crust. So it doesn't matter what continent you're on, if you were to dig deep enough down into our crust, you would find that almost all of the rocks present under our continents are felsic. And we're going to see that this is going to be very different from our oceanic crust underneath our oceans. And those are generally going to be our basaltic or our mafic rocks. Again, these are the ones that are going to be very dark in color, and they're also going to be a lot heavier because they have metals inside of them. So here we're calling these mafic because they have a lot of magnesium and iron. Ma for magnesium, Fi for iron, or ferrum, a very specific type of iron. So again, we're just getting the name here by abbreviations of what kind of elements are inside of them. But here the iron is going to be very important. These basaltic or mafic rocks are not only darker in color, but they're going to be heavier in weight and denser than our felsic rocks because now they have a lot more metal instead of salts inside of them. So again, with our basaltic rocks, there will be some lighter colored minerals inside of them. But we're looking to see primarily, is this rock light or dark in color? So if we're to look at this image of basalt, a very common oceanic crust rock, we're going to see that predominantly it's black minerals. We'll see that there are some white minerals present, but again, it's less than 10%. So if it's less than 10%, we're not really going to worry about it. Predominantly, this is a dark colored rock that is rich in magnesium and iron. But we also have those intermediate rocks, the ones that are not primarily light or dark. It's going to be a mixture between the two. So we can call these intermediate or andesitic rocks. And again, these are just going to fall directly between our felsic or granitic and our mafic or basaltic rocks. So basically, it's just a mixture of light and dark colored minerals. Now it's not going to be 90 and 10% light versus dark. Now it's going to be about 50-50. Or it could be a very medium shade of gray overall. And then our fourth and final type of igneous rock are those ultramafic rocks. These are the ones that are always going to be green in color. And that's because they're full of olivine, that olive green colored mineral. But these ultramafic rocks are going to be very unique because they're almost entirely iron. They don't actually form at the surface of our planet, but instead they form inside of our mantle, where that magma is just flowing around deep inside of the earth. So these ultramafic rocks, they're fairly rare because, again, we need uplift to push these rocks up from the mantle up to the crust where we live. But the dead giveaway that you're looking at an ultramafic rock is, again, that green color because it has so much iron and so much olivine, the mineral inside of it, giving it that green appearance. So those were our different types of rocks. This isn't a chemistry class, so I don't want to get too into the chemistry of our rocks. What we're going to focus more on is the texture of our rocks. Basically, what size, what kind of shape, and how are these minerals arranged inside of the rocks? Basically, what does the rock look like? But the texture is going to tell us a lot about how and where this rock formed. So, for example, if we see an igneous rock with very large, obvious crystals inside of it, that's going to tell us that that cooled off very slowly. Each individual mineral had enough time to grow that, like trees, it could just keep adding layers on to the sides or the exterior of those minerals. So large minerals just tell us that it cooled off very slowly before it turned into a solid rock. And we're generally only going to find this really slow cooling deep inside of our planet. The deeper we go towards our core, the hotter it's going to be. And when it's a hotter temperature, it's just going to take things a whole lot longer to cool off. So imagine that I tried baking something in my oven, and instead of pulling out my baked goods and letting it cool on the counter, I'm just going to let it cool off inside of the oven. It's going to take hours for that oven to cool off because it's very high temperature. So if we see a rock with these really large crystals, it's not only telling us that they cooled off and grew very slowly, but they also cooled off and formed deep underneath our crust. So larger crystals, again, just telling us slow cooling beneath the surface of the earth. Those are going to be our intrusive igneous rocks. But we see a lot of other types of textures with our igneous rocks. On the opposite end of the spectrum, we're going to see something that's called fine-grained. Fine-grained just means that the minerals or the crystals are just going to be very, very small in size. Generally, these are going to be so small that we're not going to be able to see the minerals with our naked eye. Instead, we're going to need to have a microscope in order to see them. So, if we were to look at this black rock here at the top, this is a good example of a fine-grained igneous rock. Although it's full of minerals, the minerals are so small that we can't see them with our eyes alone. So these very small crystals are telling us that these crystals did not have enough time to grow to be large in size, which therefore tells us that they cooled off very, very quickly and generally at the surface of our planet where it's a lot cooler. So now instead of letting my baked goods cool off inside of the oven, now I'm going to pull them out and let them cool on my counter. Now when it's in my 73-degree home, it's going to cool off within a matter of minutes instead of a matter of hours. So these fine-grained textures, again, the minerals are too small to see without a microscope, and that fine-grained texture just tells us that cooled off very quickly at the surface of the earth, before the minerals had enough time to grow in size. But our coarse grain texture is something that we've talked about so far. Coarse grain just means that the minerals are large enough that we can easily see them with our naked eye. Because they're large, they're coarse grain, this tells us that these minerals solidified not only slowly, but deep inside of the earth while they're insulated by all these really hot rocks surrounding it. But if we look closely at these coarse grain textures, we'll see that all of the minerals interlock together. So think about just putting together like a jigsaw puzzle. Even though the puzzle pieces have some jagged edges, they all fit together perfectly. They interlock together as pieces to form one large puzzle. And with these coarse grain textures, we can very clearly see these interlocking crystals that are all large enough that we can see without a microscope. Again, because coarse grain cooled off very slowly deep inside of our very hot planet. But we're also going to see a mixture between our coarse and our fine-grained igneous rocks. And this texture is called porphyritic. So if we look closely at this image, you'll see that there are some larger black and white minerals inside of it. Those would be the coarse-grained minerals. But separating these larger crystals, you'll see this kind of medium shade of gray separating them. And within this gray, these are very fine grained crystals. So with this porphyritic texture, we're seeing both coarse and fine-grained minerals, both large and small minerals inside of it. So these large crystals, so like these large black crystals that we can very easily see, these are called phenocrysts. And then the gray material separating them is called the ground mass. So the way these porphyritic textures develop is that we're actually going to see two stages of cooling develop. The first stage, this magma is going to be cooling off very slowly inside of the earth. And these large phenocrysts are going to start developing. But then something is going to happen, and it's going to force this magma up to the surface of our planet, where it's going to start cooling off a lot more quickly at the surface. And at this point, this is where our fine-grained ground mass is going to start developing. So this porphyritic texture, where we see both large and fine-grained minerals, it tells us this rock cooled off in two different stages. It started off cooling very slowly deep inside of the earth, forming the larger crystals, and then it was pushed closer to the surface, where it started cooling off more rapidly, and the minerals that developed were much smaller in size. They developed as the ground mass. But we're also going to see very specific types of extrusive textures. These are the ones that are forming from lava at the surface. And one of these is just called a vesicular texture. And this is because these rocks are full of vesicles, or air holes, inside of them. So if you've ever gotten a pedicure, you're going to have your foot scrubbed with a very vesicular rock called pumice. If you've ever held pumice, it's incredibly lightweight because it's mostly air that's been trapped inside of this lava before it cools down. So we're generally going to find these vesicular, these very holy rocks in lava flows, where lava has erupted on the surface and it's literally just flowing across the ground. Because this 1,000-degree lava is now around 70-degree air, it's going to start cooling off and solidifying very, very quickly. All of the gas that's found inside of the lava is going to be trapped inside. So when the lava hardens into a solid rock, all of the dissolved gases are going to be trapped inside of that rock, therefore giving it this kind of holy texture. When you look at these rocks, you're going to be able to see the actual holes or vesicles inside of them. So this slide is just showing us a couple more examples. Here on the top left, we see the phenocryst, these coarse-grained minerals that are developing first very deep and slowly inside of the planet, and then a very fine-grained ground mass separating them, where this magma has now been pushed up to the surface where it's going to cool off very quickly, forming very small minerals. So again, this porphyritic texture, just 2 stages of cooling. And then here on the bottom right, we're looking at a lava flow. We'll talk about this more in a couple chapters, but a lot of our volcanic eruptions, we're going to see that lava is literally just going to flow across the surface of our planet. And because it's really hot lava in contact with relatively cool air, it's going to start solidifying within a matter of minutes. It's going to cool off quickly enough that all of the dissolved gases inside of that lava are going to be trapped inside, forming rocks that are just full of holes or vesicles inside of it. But with our last 2 types of igneous textures, these are going to be very unique textures. So the first one is called a glassy texture. And we see it here with this rock that looks like a piece of black glass. So here we see that these glassy textures develop whenever a rock cools instantly. So here, this instant part is incredibly important. Not even a second has gone by to allow minerals to grow inside of this lava. And this is because we're seeing lava basically entering in really cold ocean water, where it's just going to shock that lava into instantly being a solid. Therefore, the ions inside of that lava have not even had a second to start arranging themselves in that repeating crystalline structure, those repeating shapes inside of the minerals. So if it doesn't have that crystalline structure, one of the 5 main characteristics we need in order for something to be considered a mineral, therefore these glassy textured igneous rocks technically don't have any minerals whatsoever inside of them. And again, that's because they formed instantly. The elements and the ions inside of that lava didn't even have a second to start arranging themselves in that repeating crystalline shape. And our last type of igneous texture is called pyroclastic. These are generally going to be created during very explosive volcanic eruptions. So think about one of those Michael Bay movies, where the volcano is literally just going to be blown apart like it was full of dynamite. When we're trying to break apart rocks, it's going to break into really jagged fragments, basically just broken, rough pieces of rock. But during these really explosive volcanic eruptions, it's also releasing a lot of heat. So it can basically weld all of these broken rock pieces back together as one rock. So these pyroclastic or fragmental textures, if you look closely at the rock, you'll see that all of the pieces inside of it have very jagged edges, where they've all just kind of been broken apart, and then due to the extreme heat, kind of welded back together as solid rocks again. So this chart is just summarizing the different textures and exactly what it can tell us about the environment that these rocks formed in. We're going to see, again, rocks are either going to be intrusive, forming inside of the earth very slowly, or they're going to be extrusive, where they've exited, now they're on the surface of the earth, and they're going to be forming a lot more quickly. So with our glassy texture here, again, it's very important to know that these form instantaneously. Not even a second has gone by to allow the ions to start arranging themselves in that repeating shape. So these glassy textures don't have any minerals whatsoever inside of them. Another extrusive igneous rock are our vesicular textures. Again, these are the ones that are full of vesicles or air holes because they cooled off in a matter of minutes and trapped all of those dissolved gases inside of it. We'll also see pyroclastic textures. Again, only in those really explosive, very violent volcanic eruptions, where we're literally going to explode the volcano, and the heat from that explosion is going to basically glue all these broken rock pieces back together. And our final extrusive rock is just going to be our general fine-grained texture, the ones that cooled off rapidly, and we're going to need a microscope in order to see the individual crystals. But we also have those intrusive igneous rocks, the ones that form very slowly deep inside of the earth, which are our coarse-grained rocks. These are the ones where the minerals are going to be very obvious. We're going to be able to see them with our naked eyes alone. And then finally, we have our porphyritic texture. And this is the one that's both intrusive and extrusive. It has that 2 stages of cooling, where it starts off cooling very slowly deep inside of the earth, and then it's been uplifted. It's been pushed to the surface, where it's going to start cooling off more quickly, and you're going to get that very fine-grained ground mass separating each of these larger crystals or phenocrysts. So with our igneous rocks, we're going to name them based on a combination of their texture, those 6 different textures we just saw, and their mineral or their chemical composition. Again, this isn't a chemistry class, so I don't want you guys to worry too much about the chemistry. So for the mineral composition here, we're basically going to look at the color of our minerals. Again, going back to that felsic, intermediate, mafic, and ultramafic, whether they're light, dark, in between, or green in color, is basically how we're going to cover this mineral composition. And this mineral composition is basically what exactly is dissolved inside of this magma and what kind of environment did the minerals start to crystallize or grow in. But we also need to look at the texture of these rocks. And again, the texture is just coming from the cooling history. How quickly or how slowly did it cool off, as well as where did it cool off, inside or outside of the earth. So we're just going to use this igneous rock to identify different types of igneous rocks based on the texture that we see here and the mineral composition. And again, in this class, I basically want you to focus on the color. Is it light in color, felsic? Is it dark in color, mafic? Neither light nor dark, just right in between, which is intermediate? Or is it green, which is ultramafic? So, for example, if we were looking at a very light-colored rock, a felsic rock, that was also coarse-grained, we would be able to see the minerals with our naked eye. We would be able to figure out that this rock is called granite. And granite, right now, is a very common rock. You see it in a lot of restaurants, a lot of kitchens, and even a lot of bathrooms today. But let's say that we're looking at a very dark color or mafic rock that's full of air holes. We know that air holes mean that it's a vesicular texture. So if we look at our vesicular row and we come down from mafic or those darker colored rocks, we'll be able to figure out that this rock is called scoria. So with this chart, it's generally not very hard to use. You just need to narrow down what mineral composition are you looking at. Is it light, dark, in between, or green? Then you also want to figure out which of the 6 textures this igneous rock has, and just see where the texture and the mineral composition cross in order to name that igneous rock. So now we're just going to briefly go over some of these really common igneous rocks. Again, granite is something that we see all the time right now. But granite is very coarse-grained. When we look at this image, we can easily see the individual minerals without the need of a microscope. Because it's coarse-grained, this tells us that granite forms off very slowly deep inside of the earth as an intrusive rock. Because it's forming deep inside of the earth, we need some kind of uplift to happen. These rocks literally have to be lifted up from deep inside of the earth towards the surface, which generally happens during mountain building. But granite is a felsic rock. You'll notice here that there are some dark-colored minerals, but again, it's a very small amount in comparison to the overall rock. So even though granite does have some of these black minerals inside of it, the majority are kind of those feldspars, those light pinks, and then quartz, these white-colored minerals. So overall, granite is felsic. It is light in color. Another common igneous rock is called rhyolite. This one is also felsic. It's very light in color. But if you look at this rock, the majority of the minerals are very fine-grained, meaning that we can't see the minerals with our naked eye. Instead, they're so small that we need to have a microscope in order to view them. So because these minerals are so small, it tells us that rhyolite forms very quickly at the surface. It's formed from lava that has exited the earth. It's an extrusive igneous rock. And with these, we're going to commonly see some voids or just some small holes inside of the rock, or we might see fragments of little pieces of glass. But again, if it's just one or two small pieces inside of our rock, we want to ignore those. On the whole, this piece of rhyolite is very fine-grained. We cannot see the individual minerals within it. Obsidian is probably my favorite igneous rock. This is one that forms instantaneously. Again, that instant part is very important because it doesn't have any minerals inside of obsidian. It's just a piece of volcanic glass. And obsidian is kind of weird because it's dark in color. But if we were to look at the actual chemistry of obsidian, it's full of silica because it's glass. So it's actually felsic chemically, even though it's darker in color. But the most important thing to know about obsidian is that it forms instantaneously. There are no minerals whatsoever inside of this volcanic glass because not even a second passed to allow those ions to start arranging themselves in those repeating atomic shapes. Pumice is another igneous rock that we might have encountered in our normal lives. Pumice is the one that's vesicular in its texture. It's full of these vesicles or air holes where all the gas got trapped inside of that lava and it cooled off within a matter of minutes, trapping the gases inside, which basically formed holes inside of the rock. So pumice is unique because it's one of the only rocks on our planet that can float in water. And this is because pumice is 90% air and then 10% of a rock surrounding these air holes. So because pumice has so much air inside of it, if you drop it into a bucket of water, that rock is actually going to float towards the top of the water. Both of these igneous rocks, andesite and diorite, are a little bit less common, but they're very good examples of those intermediate igneous rocks. The ones that are either going to have a 50-50 ratio of light and dark colored minerals, like we see here at the bottom with diorite, which is a coarse-grained rock. It forms deep inside of the earth, very slowly over time, causing the minerals to be large enough that we can see them with our naked eye. But again, if you look at this sample of diorite, you'll notice that it's about a 50-50 ratio of white and black colored minerals. Therefore, it's intermediate in its mineral composition. But if we look at the top, at this andesite, again, it's intermediate, but now this is kind of like a medium shade of gray. It's neither light nor dark gray, so it's just intermediate. But andesite is one of those that's commonly porphyritic, where it's going to have both coarse and fine-grained minerals inside of it. So with these, both basalt and gabbro, these are going to be our mafic igneous rocks. These are very dark in color. So when we're looking at basalt, this is the most common extrusive igneous rock found on our planet. And it's going to make up almost the entire oceanic crust. So if we were to go diving in our oceans and go from the surface waters and then dive all the way down to the crust, we're going to see that most of our oceanic crust is made out of this one type of rock called basalt. It's dark in color, and it's also heavy and very dense, again, because it's full of all of those metals. But if we look at this mafic rock along the bottom, this is called gabbro. This one's a little bit more difficult to identify, but it's a very coarse-grained rock. That means that the minerals are large enough to see with your naked eye, but because all of the minerals are black in color, It's a little bit difficult to see where one mineral starts and another mineral stops. Because this is an intrusive rock that forms very slowly deep inside of the earth, gabbro is not really common at the surface. Again, any rock that forms deep inside needs uplift to occur. We need to lift those rocks up towards the surface. But gabbro is still a really common component of our oceanic crust. But basalt is the most common rock within our oceanic crust. So we can see that igneous rocks can form from different types of magma. And we can have different types of rock forming from the same type of magma. And this is because magmas evolve over time. And we're going to see something called Bowen's reaction series developing, which is going to tell us in which order minerals are going to start developing as we go from really hot magma or lava, and then it starts cooling down over time. So we're going to see that there are specific temperature ranges that certain minerals form in. Some minerals might start forming when that magma is still incredibly hot. And then very different minerals will start forming once that magma has cooled off several hundred degrees, maybe even thousands of degrees. So this Bowen's reaction series is just going to tell us in which order we're going to start seeing minerals start to solidify and grow at very different temperature ranges as we go from really hot magma and then start cooling it down so that it can start solidifying into solid igneous rocks. So with this Bowen's reaction series, it actually tells you the order that the minerals are going to develop in. But this is a little bit more in depth than what I really care to go into for this class. So instead of learning these dozen or so minerals in the order that they start and then end up crystallizing in, I want you to focus instead on the order of the composition. What types of rocks are going to develop in which order? If we look at this temperature on the left-hand side, we'll see that really hot temperatures of magma. The first minerals that are going to start developing are going to be these ultramafic minerals. Again, the ones that are green in color, mostly because they're made up of that mineral olivine. So we're going to see these ultramafic rocks start forming when this magma is still incredibly hot. But as this magma starts to cool off over time, we're going to start seeing other minerals developing. As it gets a little bit cooler, we're going to start seeing these mafic minerals starting to develop. Those that are darker in color, usually like charcoals to black. But here, they're still full of metals. They just don't have quite as much iron inside of them. But as we continue to crystallize these minerals that are full of iron and other metals, that means that everything that's left dissolved inside of the magma is now going to be depleted in metals. That means that since the metals have solidified out, they're no longer inside of that liquid. So what's going to start crystallizing next are going to be our intermediate minerals, the ones that are a combination of metals and salts. That's because we're now running out of metals. So we're going to start incorporating some salts inside of these minerals, leading to those intermediate, both light and dark in color, because it's both minerals and salts inside of those minerals. And then at our coolest temperatures, right before this turns into a complete solid rock, the last type of minerals that are going to develop are going to be our felsic minerals, those that are light in color, lightweight, and full of salts. So again, for our Bowen's reaction series, don't worry about memorizing what order the minerals come in. I want you to know which order the composition will develop in. It's always going to start off at really high temperatures with ultramafic, and as it cools down, it's going to go from ultramafic to mafic, intermediate, and then finally, when it's cooler temperatures, our felsic minerals are going to develop. So this is just a type of magmatic differentiation. This just means that within a magma, that over periods of time, we're going to start seeing different minerals developing. Because as these minerals start to crystallize and they turn into solids, whatever elements are inside of those minerals are being removed from the magma. So if we have a magma that's full of both iron and let's say calcium, a salt. As we start removing that iron out and turning it into solid minerals, that means that the rest of the magma is soon going to be deficient in iron. It's just not going to have a lot of iron left dissolved inside of it. But instead, as we start removing more and more iron, we're going to start seeing that predominantly our magma is going to turn into calcium, that's salt. So this magmatic differentiation is just showing us that from a magma, we can get a lot of different types of rocks forming from that magma over different periods of time as it cools off from really hot magma into a lot cooler magma. But we can also see something called crystal settling occurring. And this is just when our minerals get really large and heavy. And these are solid minerals trapped inside of melted rock. So because the minerals are solid, and we're talking about a liquid rock, these dense minerals are just going to start sinking towards the bottom of our magma chamber. They're just going to settle out along the bottom. And we can see that here. We're looking at a magma chamber underneath a volcano. So think about a cave, but fill that cave entirely with really hot magma. So we know that over time, we're going to get different minerals developing in our magma. The first ones that are going to develop are going to be our ultramafic minerals, those that are green in color, because they're chock full of iron and that mineral olivine, that green mineral. So we initially start off with just one giant magma chamber. But as the edges of our magma chamber start to cool off, that's where we're going to start forming those ultramafic rocks first. We're removing all of the iron from the magma. Now that iron is just going to be stored as solid minerals outside of the magma chamber. So over time, as this magma chamber gets smaller and smaller, because the edges of it are cooling off and turning into solid rock, eventually the magma that's left inside isn't going to have a lot of metals inside of it. Instead, it's going to be full of salts and silica. We're going to be switching into developing those intermediate and then finally those felsic minerals, following that Bowen's reaction series. So before we can get into sedimentary rocks, we need to talk about weathering. So weathering forms from weather. Everything on the surface of our planet is constantly being weathered down. Don't think about things in terms of human timescales. Think about our planet over hundreds of thousands, millions, even billions of years. If something is sitting on the surface of our planet for billions of years, the weather, whether it be wind, rainfall, or even just gravity, is going to start affecting these rocks. So weathering, we're basically just breaking down our rocks over long periods of time when they're at the surface. But we're going to have two different types of weathering. We have mechanical weathering, which is just physically breaking these rocks down from larger pieces to smaller pieces. And then we also have chemical weathering. So with chemical weathering, we're not actually breaking it down into smaller pieces. But think about if you've ever seen a piece of metal covered in rust. That rust is a chemical reaction with the metal and the oxygen in our atmosphere. It's eroding or breaking down that metal over long periods of time. And this is just a good example of a chemical weathering. We're not physically breaking it down, but we're kind of breaking down the surface of that material, which is going to cause it to change the way that it looks. But generally, we're going to see that the mechanical, actual physical, and the chemical weathering are going to happen simultaneously. They're going to happen side by side. And then eventually, when we have these weathered rocks that have been changed either in their size or in their surface appearance, we're going to see that erosion is going to happen. We're going to have something move these broken rock pieces into a new area. It could be a river transporting pebbles. It could be gravity pulling rocks down the side of a mountain. But erosion just means that we are moving these broken rock pieces somewhere else. So with mechanical weathering, again, this is physical weathering. We're just breaking these rocks down from larger rocks down to smaller pieces of rock. But if I take a giant piece of rock and I break it into 5 smaller pieces, it's going to keep all the same physical properties. So if I have a big chunk of granite, for example, and I break it into 5 smaller pieces, those 5 pieces are still all going to be granite. They're all going to be very hard and resistant to high temperatures. So we're going to see that even though we're breaking our rocks down into smaller pieces, each smaller piece is going to keep the same physical properties of that original rock. The main difference, though, is that as we get into smaller and smaller pieces, we're going to see that the surface area of these rocks are going to increase. So if we look at this cube of rock here, it's a fairly large-sized piece of rock. And the majority of the rock is being protected inside. It's not exposed to the surface of this cube. But as we start breaking down this cube into smaller and smaller cubes, now all the rock that used to be protected in the middle now is a smaller piece that has its own edges. So as we get into smaller pieces of rock, it's going to increase the surface area. And as we increase the surface area, that means that more chemical weathering can happen. Again, chemical weathering is just kind of breaking down the surface of a material. Again, just like rust on the surface of a piece of metal. So as we continue mechanical weathering, it's going to allow more chemical weathering to happen. And this is why these two processes generally happen simultaneously. So just going over a few different examples of mechanical weathering. The first of which is called frost wedging. And we don't really see it here in Florida, but if we were to move to a colder location where it freezes overnight, we would see frost wedging occurring. So with frost wedging, it's just differences in the properties of water between liquid and solid water. Here we're looking at an image of a glass bottle with solid ice inside of it, and it's broken. So whenever liquid water freezes into ice, it expands out. So if we were to completely fill a glass bottle with water, stick it in our freezer, the next day that's going to be a broken glass bottle because the ice is going to expand and break the bottle. And we see the exact same thing happening inside of our rocks. In really cold locations, if some liquid water were to get inside the cracks inside of our rocks and then freeze at night, every time that water freezes in the cracks, it's going to push that crack open just a little bit wider and wider and wider until eventually the entire rock is just going to break into multiple pieces. And a similar thing that we're going to see is called sheeting. So with sheeting, we're generally going to see this with our igneous rocks that form deep inside of our planet, these intrusive igneous rocks. When they are intrusive, we can see this kind of dome-shaped intrusive rock here. But on top of it, we see that there is a lot of dirt and other materials. The weight of all of this material is just pressing down on top of this intrusive igneous rock. It has a lot of pressure, just squeezing it in. But we also know that everything on the surface of our planet is constantly being weathered. That means that all of the ground over long periods of time is going to be removed. So now if all of this sediment and dirt on top of this intrusive rock is now removed, now that intrusive rock is actually at the surface. That means it no longer has all of that weight pushing down on it. Now, because all this weight has been removed, it's kind of like that feeling when you have the weight lifted off your shoulders. And you're actually going to be able to just kind of move your shoulders back and expand out. These rocks are going to do the same exact thing. When we remove all the pressure that's squeezing them in, the rocks themselves are now going to start expanding out. And it's going to lead to what are called exfoliation domes. We're going to see entire little sheets, kind of like sheets of paper, of these rocks sliding down the side of these intrusive rock structures once they're actually exposed to the surface. But we're also going to see that plants and animals have a huge play in our mechanical weathering. When we look at this image, we can see that the tree is not just growing inside of some grass and dirt. Instead, it's growing inside of solid rock. So every year as this tree grows, its roots are going to get deeper and deeper. We can see this crack that's developing in the rock as the roots break it apart so that they can grow more. And this is just called root wedging. The roots of these trees are just going to break into the rock and wedge it apart as it continues to grow. If this tree survives long enough and the roots get long enough, eventually this crack is going to get so wide and so deep that this entire chunk of rock is just going to fall off the surface. But in addition to our trees, we're going to see animals having a big important part of mechanical weathering as well, especially animals that burrow, that dig inside of the ground, whether it be worms or, in my case, I have a lot of armadillos in my backyard that are constantly digging holes. As they're digging holes through the ground, they're increasing the surface area of that sediment that's being exposed to our atmosphere, which is going to start increasing the amount of weathering that's going to occur. And finally, all organisms, whether they're plants or animals, once they die, they start decaying. And as we decay, we start producing acids. So this acid is going to start chemically weathering things down. Think about if you were to literally throw acid on something, you are going to change the surface of that material. So let's say that this tree dies. It's going to turn into acidic material, which can chemically weather the surface of whatever it's laying on top of. But we also see a lot of chemical weathering occurring. So with the chemical weathering, we're not just breaking these rocks down into smaller pieces, but breaking them up. We're actually chemically changing these rocks. We might be removing or adding some elements. So for example, with that rusted metal, we're just adding more iron onto the top. We're changing it by adding more elements to it. But acid, for example, can start removing or eating away some of those elements inside of it. But chemical weathering generally is going to affect the surface the most. So as we start breaking down the surface of rocks, it's going to make it a little bit weaker. It's going to be easier to break that rock up by mechanical weathering. So again, we see that mechanical and chemical weathering generally happens hand in hand or simultaneously. So when we think about chemical weathering, we might think about acid being like one of the most important ones. But actually, it's just water, what we drink and use every single day. Water is made up of hydrogen and oxygen. So the oxygen that's dissolved in our water is going to cause oxidation. Oxidation is the same chemical process that's going to cause that metal to rust over time. We're going to have oxygen in our atmosphere that's just going to chemically alter the metal through oxidation. But within our water, we also have carbon dioxide dissolved, the same gas that's dissolved inside of soda and beer. But whenever we have carbon dioxide dissolved in our water, this forms a very, very weak type of acid called a carbonic acid. That's why your dentist might tell you that you need to lay off on acidic foods like wine or coffee, because that, even though it's very, very weak acid, it's not going to burn your skin. If you consume enough wine or coffee, that carbonic acid is going to start chemically weathering or breaking down the surface of your teeth. But on our planet, we have one mineral that's almost completely resistant to chemical weathering, and that's quartz. Remember, quartz is that mineral that is incredibly hard, has a hardness of 7, so you can scratch glass with it, and it also has that conchoidal fracture. Quartz is one of the most common minerals on our planet, and it's one of the very few that's just totally resistant to chemical weathering. It doesn't matter if you submerge it in water, if you dissolve a lot of gas, acids inside of it, or even if you just dump it inside of an entire vat of acid. Quartz will not be chemically weathered, unlike the majority of other minerals. So now we're just going to get into the different types of sedimentary rocks and the processes that we need to actually transform something into a sedimentary rock. So with our sedimentary rocks, this happens because we have weathering along our surface. Again, over millions and billions of years, the rocks that are sitting on our surface are not stable. They're constantly being broken down by weather. So whether it be rain falling, the wind moving, or gravity pulling things downwards, we're always going to see that weathering is going to break rocks down into smaller pieces. But generally, we're going to have erosion occurring after weathering. So weathering is just breaking the rocks down. Erosion is moving those broken rock pieces somewhere else. So think about a really sharp mountain peak. Over long periods of time, it's not going to stay a nice sharp mountain. Instead, the top part of your mountain is going to start being weathered down. We're having rainfall, we're having wind slam inside of it, and then you also have gravity trying to pull things straight down. So over time, this very sharp peak mountain is going to turn into kind of like a rounded hill. And all of the broken material from that sharp peak is just going to be pulled down the side. It's going to be transported somewhere else through erosion, where eventually all of that erosion is going to be deposited as sediment. So we're going to talk about sediment a lot throughout the rest of the semester. Sediment is just a fancy way of saying dirt. If you were to go outside and dig in your yard, you would actually be digging through the sediment. Sediment is just tiny broken down pieces of rocks that have been transported somewhere else. But with our sedimentary rocks, they're deposited layer on top of layer. So think about the Grand Canyon. You have these stacks of rocks, just one on top of another. And this is how sedimentary rocks develop. We're going to start depositing sediment layer by layer, one on top of another. And as we start burying all of the sediment underneath all of the layers on top of it, it's going to start pressing down on it. And it's going to lithify that sediment. It's basically going to glue each individual little piece of sediment together as one solid rock. So with these sedimentary rocks, it's kind of a complex list of things that need to happen. But sedimentary always form from breaking down pre-existing rock pieces, moving those broken pieces somewhere else through erosion, where they're going to be deposited, buried, and then eventually glued together or lithified as a solid sedimentary rock. So that's how the majority of sedimentary rocks form, just breaking down and then gluing back together these other rock pieces. But we're also going to see that some sedimentary rocks form from solid material settling out of a fluid. And this might sound weird, but there's some common examples in our day-to-day lives that we'll get into in just a couple of slides that'll make this a little bit easier to understand. But sedimentary rocks are kind of rare. We're going to see that with the majority of our planet, if we're looking at the outer parts of the crust where we live, sedimentary rocks only make up about 5% of our crust. But if we were to look at rock outcrops, things like the Grand Canyon, where we can see all of these layers of rocks, the majority of these rocks are sedimentary rocks. So even though overall they're a very small proportion of our planet, where we live, a lot of the rocks that we see, even just driving down the highway, are going to be sedimentary rocks. And sedimentary rocks are going to be really, really important, both economically and trying to figure out the past of our planet. So with sedimentary rocks, these are going to be the type of rocks that fossils will form in. So with fossils, it's going to tell us a lot about the history of our planet. We might find dinosaur fossils or maybe even human fossils. But these rocks can also tell us a little bit about the environment that they formed in. And we'll get into this a little bit more later as well. But sedimentary rocks are also incredibly economically important. So a lot of the things that we use for energy, whether it's coal for electricity or the petroleum in our cars, the natural gas, fueling our stovetops, all of these energy sources are found inside of sedimentary rocks. But we also find a lot of other things like our metals that we use for electronics, the fertilizers we use in agriculture, and just our overall construction materials inside of these sedimentary rocks. So again, they make up a small amount of our planet, but they're incredibly important both economically and helping us figure out what the Earth has been like in the past. So with our sedimentary rocks, we're only going to have two different types of textures or groups to break them down into. We saw 6 with igneous rocks, but sedimentary rocks are going to be a little bit easier to deal with. So here our two main groups are either detrital sedimentary rocks or chemical sedimentary rocks. So these detrital rocks are made from pre-existing rock pieces that have all been broken down and then lithified or glued back together. So with detrital sedimentary rocks, they're just made up of multiple rock pieces or particles inside of it. Our chemical sedimentary rocks are going to be very different. Here, this is where we're going to have solids settling out of a solution, or just solids slowly sinking towards the bottom out of a liquid. So starting off with these detrital sedimentary rocks, these could be made up of any type of pre-existing rock pieces. So there's a large variety of different types of minerals that we're going to find in these detrital rocks. But for the most part, we see that clay and quartz are the most common minerals inside of them. So this chart is just showing us different detrital sedimentary rocks and how they're differentiated from one another. So when we were looking at igneous rocks, in order to classify them, we wanted to look at the texture and the mineral composition. But here with our detrital rocks, what we want to look at is what size are those particles inside of the rock. We're going to see that some are going to be very coarse pieces of pre-existing rock, so like pebble size. We're also going to have some that are smaller, that are sand-sized particles, just like the pieces of sand we would find on the beach. And we can also get into really fine-grained pieces of rock. Pieces that are so small we need a microscope in order to see each individual mineral. So these detrital sedimentary rocks, again, they're made up of these pre-existing broken down rock pieces. But these rock pieces can go from microscopic up to large pebbles in size. But looking at the size of these particles is also going to tell us what kind of environment these particles were deposited in when they were just left behind. So we're going to see that the larger the particle is, the heavier that particle will be. So we're going to see differences in the amount of energy in these environments. So for example, if we're looking at a really fast-moving river, that fast-moving river has a lot of energy inside of it, meaning that it has the energy to move larger, heavier particles, like these coarse-grained detrital rocks at the top of this chart. But if we're looking at a lower energy environment, maybe like a small trickling stream, because that water is moving more slowly, it has less energy. It doesn't have the energy required to move larger pieces. So lower energy environment can only move smaller particle sizes. So looking at the size of the particles within these rocks will tell us how much energy was in that environment. But our chemical sedimentary rocks are going to develop in a very different way from the detrital ones. The detrital rocks are the most common, but we do see a lot of chemical sedimentary rocks. And again, this is where we have solids forming from a solution, which sounds really complicated. But think about trying to make a pitcher of sweet tea. I went to college in Alabama, and I quickly learned that sweet tea is amazing. But since I never made it growing up, I just assumed that I could just dump a whole bunch of sugar in that hot tea, and all the sugar would dissolve. But probably the first or second time I tried to make sweet tea, I realized that there is a certain amount of sugar that tea can hold. If I just kept dumping more and more sugar inside of that pitcher, eventually the sugar, although it's going to initially dissolve inside of the tea, eventually if I leave that sitting on my counter, the sugar is going to start settling out. It's going to start falling down and then forming a layer at the bottom of my pitcher. This is exactly how these chemical sedimentary rocks form. We have a lot of ions dissolved inside of a solution, some kind of liquid. But over time, whatever's dissolved inside of that liquid is going to turn into a solid, and it's going to precipitate. It's just slowly going to settle towards the bottom. So some of these are going to be called evaporites. So this is just solid salts that have been left behind whenever salt water evaporates. So let's say I'm just going to put some salt water on my stove and I'm going to let it boil for a couple hours. Over time, as that water boils, it's going to evaporate, meaning the liquid water is going to leave the pan and all the salt inside of that salt water is going to be left behind. As the water itself evaporates, it's going to leave behind that solid material, that salt, crusting along the bottom of my pan. And that salt we're just going to call an evaporite. But chemical sedimentary rocks can get a little complicated because they have a subtype called biochemical sedimentary rocks. Here we're going to see the same thing occurring. We're going to have solids forming out of a liquid. But here the bio part is important because some kind of living organism is going to be precipitating or creating these solids. So for example, think about our teeth. Our teeth are minerals, and we are a living organism. So our bodies are creating these biochemical rocks. Even though we don't have to think about growing our teeth or our bones, everything that we eat, all of those dissolved nutrients are eventually going to be formed into solid bones, teeth, or even shells in some organisms. So these biochemical sedimentary rocks, they form in the same way as chemical sedimentary rocks. But the main difference is that now we have some kind of organism controlling this precipitation or the creation of these minerals. So we're going to see that probably one of the most common types of biochemical rocks are chalk. And we've all probably played with chalk, at least during our childhoods, or if we've had to write on a chalkboard. But what no one really tells us is that every time we write with chalk, we're actually writing with tiny shells of these incredibly small animals called coccolithophores. These are microscopic algae that have kind of a shell around them. But these algae, just like algae that you might see in a lake where it creates kind of a green surface on the lake, eventually all of that algae, those coccolithophores, are going to die. And then they're going to start slowly settling from the top of the water where they were growing down to the bottom. And it's just going to keep layering these layers of dead algae. And eventually this is going to form chalk. So every time you write with chalk, you're actually crushing the bones of this microscopic animal to leave the mark behind. So because these biochemical rocks are formed from animals, we're going to see that the majority of them form a mineral called calcite, which we talked about in our last chapter. But calcite is going to be very important because it makes up the rock limestone. And in central to southern Florida, all of our rocks are made out of limestone. It's this rock that's made from some other type of organism, whether it's these microscopic algae forming chalk or seashells and corals that are forming the rocks here in Florida. So if we want to test between whether or not we're looking at a chemical or a biochemical sedimentary rock, the easiest way to figure this out is to just put a drop of acid on them. Because limestone is made out of calcite, that mineral that reacts, it effervesces to acid. All of our biochemical rocks are going to react to acid. But our chemical sedimentary rocks are not made out of calcite. So there will be no reaction with our chemical sedimentary rocks. So with our sedimentary rocks, we're going to see a very wide selection of how they might look. So one that we're actually going to see fairly commonly here in Florida is a rock called coquina here. And it's formed on beaches that have a lot of just shells broken up that are lithified or glued back together. So if you were to look closely at coquina, you would be able to see individual, just very small broken pieces of shells that have all been glued together as a solid sedimentary rock. We also just talked about chalk, which is another biochemical rock. Here, it's not seashells that are being grown, but instead it's those microscopic algae that are growing dying, and then settling out towards the bottom of like a lake or an ocean. But we're also going to see a lot of those chemical sedimentary rocks developing, things like chert, flint, and jasper, which we can see here along the bottom. One of the things that are going to give away chemical sedimentary rocks, again, those that do not react to acid, these are going to be very smooth in texture. And that's because as the solids settle out of that liquid, they're going to be very fine grained. They're going to be microcrystalline. So if we could rub like a piece of flint or chert, it's going to be incredibly smooth to the touch. But we're also going to see salt and gypsum forming as those evaporite deposits. Again, if I'm taking water with a lot of minerals dissolved inside of it, if I evaporate that water, I'm going to be left with those solid minerals behind as an evaporite. And then finally, probably one of the weirdest types of sedimentary rocks are coal. Coal does not have any minerals inside of it because it's made up entirely of organic matter. This once living material from like plants that have formed over millions of years, and now we can actually burn this rock and use it to not only have electricity in our homes, but also ship things around the world. So with coal, again, it forms in a very unique way in comparison to all the other sedimentary rocks. But we're going to see that coal develops in 4 different stages. But all of it is going to go through one chronological order. It's going to be going from a low-grade coal, and then over millions of years, eventually it's going to be into a high-grade type of coal. But all coal starts forming in swampy environments. We're going to have plant material, whether it be leaves, plants, or trees, that are going to get trapped inside of a swamp. And this is important because if you've ever walked through a swamp, you'll notice that it's very difficult to pull your feet out of that mud. So as these plant materials fall into the mud of a swamp, they're slowly just going to be pulled farther down into that mud. And it's going to help protect and preserve that material over millions of years. So the first part of coal formation is the forming of peat. And peat's not actually a type of coal. Instead, peat is just broken down organic material. So with peat, you might actually be able to pick up a handful of peat and still be able to recognize this is a leaf fragment or this is a piece of grass inside of it. But once we start compacting peat, if we have a layer of peat, this broken down material, and we start burying stuff on top of it, all the pressure of this material is going to be pushing down on top of that peat, and it's going to start compacting it into a smaller area. So the first real form of coal that's going to happen after compaction is called lignite. And lignite doesn't even really look like coal as we would expect. It's incredibly soft, soft enough that if I had a piece in my hand, I could squeeze it and crumble it. And it's also brown in color. So lignite isn't a type of coal that we want to burn for energy. It's just going to release a lot of pollutants out into our air. But if we bury this lignite under even more material, now it's going to be under even more pressure and compaction. It's going to turn into another second type of coal called bituminous coal. This one is still relatively soft. I can no longer crumble it with my bare hands, but I can easily break it apart. And now it's going to be kind of a dull black color. Bituminous is mostly what we burn here in the United States for our electricity. But this is not yet the highest grade of coal. If we allow this bituminous coal to be metamorphosed, if it's going to be changed under intense heat and pressure, it's going to turn into its final form, which is called anthracite coal. This is going to be very dark black, and it's also going to be very shiny coal. This would be more like a food grade coal. So if you've ever been to like one of those 1,000-degree pizza places, where they're actually burning coal to create your 1,000-degree oven, they're burning this anthracite coal because it's going to release the fewest number of pollutants because it's the highest grade of coal that we can form on the earth. So this chart is just summarizing the different types of sedimentary rocks. So here, this is just looking at our chemical and biochemical rocks. And again, the easiest way to figure out which one you have is just to put a drop of acid on them. These biochemical rocks are made out of calcite. So all of the rocks that have calcite inside of them are going to react to that acid. It's going to effervesce or kind of bubble up along the surface. But all of our chemical sedimentary rocks found here at the bottom do not react to acid. So if you just need a quick and easy test to figure out whether you're looking at chemical or biochemical rocks, again, just a single drop of acid is going to be the easiest and the quickest way to figure this out. So when we're looking at how we go from that loose sediment, just that loose dirt, and how it's eventually transformed into solid sedimentary rocks, the last part that we need is called lithification. And this is just a really complex way of basically saying we're going to glue all these loose particles together as one solid rock. And lithification is going to happen in two different parts, through compaction, just squeezing all those particles closer together, and cementation, where we're actually going to form cement between each loose piece of sediment. So with compaction, again, this is all due to the fact that we're burying the sediment under layers of other sediment, just layering up one on top of another, so that these upper layers are pushing down or compacting all the layers that are underneath them. It's just going to squeeze out all of the space between particles and force them to be in a smaller area. And this is going to be really important when it comes to those fine-grained rocks, the ones with tiny little minerals, because the smaller the fragments are, the more that we can compact them together. But lithification also needs something to cement each of these individual pieces of sediment together as one solid new rock. So with this, just like the cement that we might find out in the road that's holding all these rock particles together, we're going to see the same thing occurring in our sedimentary rocks. Generally, this is just going to be from water moving through the little gaps between each sediment piece. Water is rarely ever pure. There's always a lot of dissolved things inside of our water. So this cement usually forms from whatever's dissolved in the water precipitating or turning into a solid and filling all the pores or the little gaps between each little piece of sediment, thereby gluing them all together. But cementation is going to be the most important thing when it comes to those really coarse-grained rocks. If I'm creating a sedimentary rock made out of pebbles, if I have these large pebble sizes, I'm only going to be able to squeeze them together so much. What's going to be more important is being able to glue or cement all of these coarse-grained pieces together as one solid rock. But lithification, it has those two different components, compaction and cementation. But sedimentary rocks are going to be really unique because they form these flat layers that are called strata or sedimentary beds. So probably the most obvious example of this is going to be the Grand Canyon. If you look at the sides of the Grand Canyon, you'll see that there are these clear layers of rocks just stacked one on top of another, going from the bottom all the way up to the top of the Grand Canyon. So each of these layers, again, they're just called a strata or a sedimentary bed. And we only see these layers in our sedimentary rocks. We're not going to find them in igneous or metamorphic rocks. But sedimentary rocks are also really important because these are the only types of rocks that we're going to find fossils in. And fossils are just the remains or sometimes just the trace of some kind of ancient life that's been preserved in a rock. But fossils are only found in sedimentary rocks. And this is because if we have, let's say, a dinosaur bone, and we try to put that dinosaur bone into lava so that it could eventually form an igneous rock, the heat of that lava is going to melt the bone. So there's no chance of it being preserved as an igneous rock. And we'll talk about metamorphic rocks in a minute, but they form from intense heat and pressure. If I suddenly expose a dinosaur bone to 5,000 degrees and tons of pressure, I'm going to break the bone. So it's not going to be preserved as a metamorphic rock either. But we're going to see that fossils are preserved in our sedimentary rocks. If I have a layer of dirt here, and then I leave my dinosaur bone here, and then layer it with another layer of dirt, the compaction there is going to help preserve that bone over time, making it more likely that a fossil will form. But fossils can also tell us about the ancient environment of the rocks that they formed in. So for example, if I find a fish fossil inside of a rock, I know that water of some type had to be in that environment, whether it be a river, a lake, or an ocean, because we know that fish only live in water environments. But not all of these environments are super obvious. Here we're looking at sedimentary rocks that show us what kind of environments that they were deposited in. So this larger image A is showing us ripple marks, just like ripples of water that you might see along a lake. We can see these ripple marks inside of the rocks. So the way that these rocks formed, these are very fine-grained detrital sedimentary rocks. Here, they're still made up of these individual particles, but the particles are so small that when they're wet, it's just mud. So as the water is moving across this mud, it's leaving ripple marks inside of it. Eventually, the water is going to evaporate away, leaving these mud with ripple marks in it, and eventually that mud is going to turn into solid rock. So because we see ripple marks here on A, that tells us that we have some sort of moving water in this area. B, we're still forming this from water evaporating away from mud. But what we're looking at in B are called desertification cracks. And these tell us that this rock formed in a desert or a very arid environment. So as things start to dry out, they start cracking. So here we can see where mud very quickly dried out in a very humid, arid environment. So as this mud starts drying up and turning into rock, we're just going to see a lot of cracks developing in the mud, telling us again it's an arid environment that it formed in, like a desert. So far we've covered our igneous and then our sedimentary rocks. And now with these last few slides, we're just going to go over metamorphic rocks, how they form. So with our metamorphic rocks, these are going to form in a very different way. With our metamorphic rocks, we're going to have some form of pre-existing rock, which we call a parent rock. That is going to be transformed through intense heat and pressure into a new type of rock. So with metamorphic rocks, it doesn't matter what type of rock that parent rock is. It's going to be igneous, sedimentary, or even another metamorphic rock. The important part is that intense heat and pressure is going to metamorphose or change that parent rock into an entirely different rock. So metamorphism is going to change not only the minerals found inside of the rocks, but it's also going to change the texture and sometimes even the chemical composition, what kind of elements are found inside of those rocks. But metamorphism happens incrementally, just like we saw with the development of coal. We're going to start off with these low-grade metamorphic rocks that have just had slight changes to them, and then we're going to work our way through an order to eventually end up with our high-grade metamorphic rocks, where there have been substantial changes to that rock from the parent rock to the new metamorphic rock. So with our metamorphic rocks, here we're looking at two different types, always going from a parent rock through changes that are going to turn into a new metamorphic rock. So here with A, we're looking at shale, which is a sedimentary rock. It's a detrital sedimentary rock that's made up of those really tiny, fine-grained particles. But with low temperatures and pressures from that low-grade metamorphism, just a little bit of change, we're going to turn this sedimentary shale into a new metamorphic rock called slate. And here, because it's just low-grade metamorphism, a little bit of change, they actually look very similar to one another. The main difference is that we've had more compaction from that increased pressure. We're squeezing all those particles into a smaller area, making them more tightly packed together. But we can also see high-grade metamorphism occurring. And this is from extremely high temperatures and pressures that are going to form substantial changes from our parent rock to our new metamorphic rock. So here on the left, we're looking at a form of granite, an igneous rock. But under extreme temperatures and pressures, we're going to change this into a metamorphic rock called gneiss. And with this high-grade metamorphism, it can produce something called foliation, or basically bands or layers within these rocks. So if we look at the granite parent rock before any change happened, we can see that these minerals are just randomly distributed throughout this rock. But from extreme heat and pressure, we'll see that there are these folded bands of light and dark colored minerals that are starting to separate out from one another. So again, with metamorphism, it's just changing a pre-existing rock into a new type of metamorphic rock through temperature and pressure changes. So with metamorphism, this is going to occur in two different ways. The first of which is called contact metamorphism. And this is where rocks are going to change because they're in direct contact with something that's super hot. So think back to those magma chambers that we talked about earlier. The magma chamber itself is just magma, but it's in direct contact with the rocks holding all that magma inside. So the intense heat from that magma is basically going to bake or change the rocks surrounding the magma chamber, which is contact metamorphism. But if you want a better, more basic life kind of example, think about trying to bake cookies. I am constantly trying to learn how to make cookies that are edible, but I always seem to burn them every single time. And that's because that cookie dough is in direct contact with a hot cookie sheet. And it's a metal cookie sheet, so it's going to heat up very quickly. The bottom of that cookie is going to start cooking first because it's in direct contact with that hot cookie sheet. But this is also the part of the cookie that's going to start burning first. So just like burning cookies, we can see that rocks that are in direct contact with really high heat from magma, we're basically going to cook or change those rocks through contact metamorphism. But our second type of metamorphism is going to happen in a very different way, and this is called regional metamorphism. And this one is less to do with heat and more to do with intense pressure. And we're generally going to see this regional metamorphism happening during mountain building. So it's going to happen on a regional or very large scale. We're talking about areas the size of states or even entire continents that are going to be regionally metamorphosed. But there are a lot of different things that are causing metamorphism to happen. The first of which is just heat. Just like if I were to cook some noodles on a stove, the heat from that boiling water is going to change it from that very stiff, uncooked noodle into a very soft, bendable noodle after it's been cooked. So we're going to see that heat is going to cause chemical reactions to occur, and it's also going to cause some minerals to either be destroyed or causing new minerals to form. But in addition to our heat, we also have a lot of pressure that's causing metamorphism as well. And we have two different types of pressure. The first is called confining pressure. This means that the pressure is equal in all directions. So think about if I just had a beach ball. And I held this beach ball up, and I could cover every surface of that ball with some kind of like hand, for example. And then every single hand is just going to squeeze in with the exact same amount of pressure at the same time. It's just going to cause that beach ball to get smaller. It's going to compact. Overall, it's still going to be relatively circular in its shape. We're just squeezing it down into a smaller ball. But this is very different from our second type of pressure, which is called differential stress. Here, the pressure is going to be greater in one direction than all of the others. So instead of having all areas squeezing in equally, now we're going to have some that are squeezing in a lot and then some they're just squeezing in a little bit. So this is going to cause our rocks to deform. We're going to change the shape, the texture, and the location of some of these rocks. And with differential stress, we can either break or bend our rocks depending on what kind of temperature they're in. But finally, we're going to see that chemically active fluids, like super hot water in a hydrothermal vent, can cause other metamorphism to occur. Generally, this is just going to change the chemical composition of the water and the minerals and rocks in contact with that water. So this image is just showing us the different types of pressure that we can have. Here at the top, we're looking at confining pressure. We have a cube with these nice flat strata of sedimentary rocks. But with confining pressure, on each face of this cube, we're just going to squeeze it in with the same amount of pressure. It's just going to make that cube become smaller in size. You'll notice that the strata inside are still these nice flat sedimentary layers. But this differential stress that we see on the bottom, it happens a lot around mountain buildings where we're colliding two continents together. But with this, we have one direction where the pressure is going to be a lot greater than all of the others. So now with this cube, we're going to be squeezing it in from the sides more than the other four sides. We're going to take it from being cube shaped, and now it's going to be a very thin rectangle. So it's changing the shape of these rocks, but it's also deforming or changing the rocks inside of them. Now you'll notice that these are not these flat strata anymore. They've all been folded. So we're going to see that differential stress, we're not only changing the size of our rocks through compaction, we're also deforming the rocks in the way that they appear. So with metamorphism, again, we're changing these rocks from the parent rock to a new type. And this is going to change the texture pretty significantly. But with metamorphism, again, it happens in like a very specific order. We're always going to start off with low-grade metamorphism with just a little bit of heat and pressure causing minor changes. And then we're going to work our way up into higher heat and pressure causing higher grades of metamorphism. So with low grade, since it's just a little bit of heat and pressure, we're mostly just compacting our rocks. We're taking them from a larger piece, compacting them into a smaller rock, and therefore making them a little bit denser. But with our high-grade metamorphism, now we're talking about extreme heat and pressure. We're going to do a lot more than compaction. We're actually going to cause some crystals to be destroyed, or some minerals, like the case of diamonds, they only form under these extreme pressures, which can cause growth of new crystals due to high-grade metamorphism. So when we have that differential stress, where we're going to be applying pressure in one direction more than all of the rest, it's going to lead to something called foliation to develop. In foliation, we're just causing the minerals to line up in one overall direction. So, for example, here on the left, we're looking at a form of diorite, that black and white intermediate igneous rock. Here, the minerals are just randomly orientated. So we're going to see that they line up in any possible direction. But if we start squeezing in the sides through differential stress, we're going to cause all of these minerals to line up in one overall direction. And this is called foliation. So with foliation, it might appear like pages along the sides of a book, or if it's high-grade metamorphism, we're going to see these very clear bands of light and then dark-colored minerals. So we generally see foliation developing from that regional metamorphism, where it's happening from mountain building, and we're going to have a lot of differential stress involved. So this is, again, is going to cause the minerals to start aligning themselves in one overall direction. They're not going to be perfectly parallel, but overall they're going to be lined up in one orientation. So we could see that the minerals themselves are going to align, Or in the case of very high-grade metamorphism, we're actually going to see that separation of the light and dark colored minerals like we just saw on that last slide. But not all metamorphic rocks have foliation. Some rocks are non-foliated. This means that it's just very low-grade metamorphism that has happened. It's basically compacted the rocks, but it hasn't really changed them much chemically or physically. So with our metamorphic rocks, we're going to break it down into two different textures, our foliated and our non-foliated textures. So with these, we're going to start off with our non-foliated. Again, these are low-grade metamorphism. So it's just a little bit of heat and pressure. And the most significant change is that we're just going to compact it into a smaller, denser rock. But as we move from these non-foliated rocks into our foliated rocks, we're increasing the heat and pressure. But we're going to see that these rocks are going to follow a specific order when it comes to foliation. The first type of rock that's going to be foliated is going to be called slate. So with slate, if we look at the sides, it's going to look like pages in a book lined up along the spine. It is foliated, even though the grains themselves are very fine. But if we take slate and apply more heat and pressure, it's going to turn into a slightly higher grade metamorphic rock called phyllite. And phyllite's unique because even though the minerals are foliated, they're lining up in one overall direction. The way that they line up are through these wave-like appearances. But if we take phyllite and apply more heat and pressure, it's going to turn into a rock called schist. And for me, schist looks like someone took some really big pieces of glitter and then glued it all together. But instead of just having a pile of glitter, someone meticulously stacked the pieces of glitter so they're all flat, one on top of another. But with schist, if you take this and apply even more heat and pressure, now we're into these high-grade metamorphic rocks, where the foliation is so extreme that the minerals are not only lining up in one overall direction, they're starting to separate out into different light and dark colored bands, like we see here in this rock called gneiss. The G is silent here, it's just pronounced gneiss. So when we look at these really common foliated rocks, again, it's always going to follow one specific order: slate, phyllite, schist, and then finally gneiss. So slate, it has that cleavage that we talked about with minerals. If you could look on the side and see the repeating shapes. But with slate, it's going to look just like the pages of a book from along the side. But as we take slate and apply more heat and pressure, it's turning into phyllite. For me, phyllite kind of looks like the lead inside of a pencil. It's kind of greasy looking. The book calls it glossy. I think it's a little bit more greasy. But again, phyllite is unique because it has that wavy appearance to it. Although the minerals are lined up in parallel layers, the layers are not flat. They're wave-like. But if we take this phyllite and apply more heat and pressure, now we're getting into these higher grade metamorphic rocks. And this third type is called schist. Generally, it has a lot of those mica minerals in it, so it looks very glittery. Some examples, again, it's just going to look like someone glued a whole bunch of glitter together. But if we take that schist and apply extreme heat and pressure to it, it's going to turn into gneiss. That rock where the foliation is so clear that we're actually going to have bands of light and dark colored minerals starting to separate out from one another. But gneiss is the highest grade metamorphic rock that we can form. Because if we take gneiss and apply any more heat and pressure, it's just going to melt back into magma. And eventually that magma is going to turn into a new igneous rock. So gneiss is the last or the highest grade of metamorphic rocks that we can have before we just melt that rock back into magma. So in other countries, we're going to see that slate is really commonly used, especially in mountainous areas. It's a great roofing tile, for example, because it has that rock cleavage. just like pages of a book where you can open a book just randomly to a page. With these slate rocks, you can hit them along the side, and they're just going to break into these flat pieces, which make it great to slap on your roof. And here we can just see broken pieces of the slate that have fallen off the side of a mountain. But not all metamorphic rocks are foliated. Again, with just a little bit of heat and pressure, we're going to form those non-foliated metamorphic rocks first. And here we're only going to focus on two of them, marble and quartzite. So both of these look very similar to one another. They're very coarse, and you can't really see the individual minerals inside of them. But they form from very different parent rocks. So marble forms from limestone. Quartzite forms from sandstone, just individual quartz grains. So because marble is formed from limestone, and we know that limestone is made out of calcite, marble will always react to acid. But because quartzite is made out of sand, and therefore that mineral quartz, it's not going to react to acid, but instead it's going to be incredibly hard because it's made out of all of those quartz mineral grains. So I know this is a really long chapter, but with this, I want you to get comfortable with the three different types of rocks that we have on our planet. We have igneous rocks that form from the cooling and solidification of either lava or magma. We have sedimentary rocks that either form from broken down pieces of rock being lithified together as a new rock, or having solid pieces kind of settle out of a liquid. And then finally, our third type, our metamorphic rocks, form from changes in heat and pressure that are going to metamorphose or change our rocks into something new. So with this chapter, we have the same general type of weekly assignments that will be due. You'll have your quiz through Canvas, the activity through Mastery in Geology, and a discussion post. If you have any questions for this material throughout the week, don't hesitate to send me a message in Canvas, and I'll try to get back to you as soon as possible. But good luck studying.